Right, welcome back one and all to week 2 of our discrete math journey. Plan for today will be to start by talking about what's known as logical inference rules and when they are sound and unsound. We'll talk about yet another way of proving statements by contradiction. And then we'll talk a bit about predicates and quantifiers and start with an introduction to sets, which will be mostly continued into next week. Okay, so let's get started. The first topic will be inference rules. Okay, so what is an inference rule? These are sort of rules or laws for when can you make a logical deduction. Okay, or inferring new propositions from previously proved ones. Okay, so take a look at this example here. Notationally, we write this sometimes by having this vertical bar, and above the vertical bar are listed the assumptions, and below the vertical bar is some conclusion. Okay, so for example, maybe our assumptions are that P implies Q and Q implies R, and the purported conclusion is that P implies R. Okay, so any choice of collections of propositions on the top and the bottom give you a candidate inference rule. And the question is, when is an inference rule sound, or when is it kind of correct? So formally, an inference rule is sound if whenever all of the assumptions are true, then the conclusion is true as well. And what do I mean by whenever? This is in terms of all possible assignments of the propositional variables. Okay, so if you're thinking about this in terms of a truth table, every assignment is one row in the truth table. And being sound is saying that if it's the case that for each row in the truth table, such that all of the assumptions have true, then also it must be that the conclusion is true in that row as well. Okay, so for example, going back to the previous slide, is it the case that whenever P implies Q and Q implies R are both true, that P implies R is true as well? Okay, and if you go through, I recommend you go through and do this as a mini exercise. You'll see that yes, this is a sound inference rule. Okay, a couple more examples of sound inference rules. So the modus ponens is this fancy name for the following inference rule, that if I have P implies Q is true and P is true, then also it must be, you can conclude that Q is true. Okay, another example that we've seen in the previous week is the contrapositive. If it's the case that not P implies not Q, then Q implies P. And note here, by the way, so I've previously we wrote not Q implies not P versus P implies Q, but here we're just changing the letters. There's nothing that's fundamental there. Okay, so both of these are examples of sound inference rules. I'm not going to give the proof, but this is something that you would be able to prove. On the other hand, what's an example of an unsound inference? Okay, for example, we saw in the previous class that the converse is not equivalent to an implication. And as a kind of related example here, if I start from not P implies not Q, I cannot conclude P implies Q. Okay, so what is the benefit, the usage of these inference rules? Well, in some sense, this is exactly at the core of proofs, mathematical proofs. These are exactly the steps of logical deduction that allow you to proceed in a proof from the axioms that you're starting from to the proposition that you're trying to prove. Okay, so for example, this modus ponens that we saw before, this is a sound inference rule. So what does this mean? This means, suppose that in one of my steps within the proof, that I'm able to show that P implies Q and P both hold. This allows me to take another step to conclude from this that now Q must hold. Okay, this is exactly where these steps are coming from. It's just different application of different inference rules, sound inference rules. Okay, but soundness is important. Okay, so here, for example, Let's take a look at a wrong proof. Okay, note that this is a wrong proof. Don't tune in late and think this is correct. Okay. Suppose we would like to prove that all the propositions P, Q, and R are all true. Here is a wrong suggestion to do that. Suppose that we first prove that P implies Q, Q implies R, and R implies P, and then try to conclude, thus P, Q, and R are obviously all true. Okay, so what is this attempted step? How does that translate to some inference rule? Okay, this corresponds to the following candidate here, where I didn't draw the vertical line, but again, these are the assumptions line, and this is the conclusion. Okay, so you can take a look at this, and you can ask, is this a sound inference rule? Okay, and now this is good. We'll actually see an example here, where how you can determine whether an inference rule is sound or not by one method of using a truth table. Okay, so to do so, let's write out the truth table for all these corresponding things. So note these first three columns are the three different assumptions that we had in the candidate inference rule. And this final one on the end is the P and Q and R was the conclusion. Okay, so you go through, you fill out all these columns step by step. And now I ask, is this sound? Given this truth table, what is it that you need to look for to answer that question? Okay, and remember again, so an inference rule is sound if for any assignment or any row in the truth table where all of the assumptions are true. Okay, so if you look at this middle region here, there's exactly two such rows, the very top and the very bottom. And the question is it the case that in all of those rows, that the conclusion is also true? Okay, so take a look. In the top, we're good. But in the bottom, we have that each of the assumptions are true, but the conclusion is false. What does that mean? No, it is not a sound inference rule. Okay, so these are some examples of the definition of soundness, some examples of yes sound, no sound, and now you can kind of see one approach to answering those kinds of questions. And I do want to have a bit of an aside here that maybe you've noticed this seems kind of related to implication. Okay, and in effect, they are actually quite close. Okay, so recall the truth table for implication, which now you all know and love. Okay, so here this is false only if P is true and Q is false. And now let's go back to this inference rule viewed as an implication. So what I'm saying is that the above inference rule, this general collection of assumptions, say A, B, and C, and conclusion D, is a sound inference rule if and only if the proposition, okay, here this is where the implication is coming in, and the implication takes all of the assumptions and sticks ands between them, implies the conclusion. Okay, so if and only if this proposition is always true, that is, it's true for all possible assignments for the entire truth table. And again, so kind of what's the intuition here? This is saying indeed that whenever you have that A is true and B is true and C is true, then necessarily you should also have that D is true as well. Okay, so the inference rule is sound is in fact another way kind of saying that this proposition always holds. All right, this concludes this unit about inference rules. And don't forget to take a look and do the quiz before continuing to the next unit.